All right, welcome to part 2 of our Module 1 lecture. This is looking at the foundations of sound research. Primarily, we're looking at study design and how we ensure that the measurements we are collecting have all three qualities of good data, meaning that they are reliable, they are valid, and they are objective. Just a brief intro into the types of research that exist. Okay? Research is basically just a technique that we use to solve problems that are unanswered by common or expert knowledge. Okay? So there are different types. There could be historical research, which is looking at past events or predictions maybe of future events based on past or present problems. We're not interested in historical research, not primarily at least. You could incorporate this into our type of experimental research in terms of disease progression or past diseases if you're researching diseases. We also have observational or descriptive research, which is where you as the investigator go out into some environment, whether it's controlled or not, and you describe what the conditions are, you describe what is happening within that environment. Generally, conditions are not intentionally manipulated, but if you wanted to know maybe how a child interacts, in certain conditions, that could be observational research. Some of you might be familiar with the monkey research, and I'm blanking on who conducted this study, but it has to do with the nurturing effects on behavior. And so somebody put monkeys in different cages, one where they had like a wire mother that had like a soft texture to it versus basically having no soft texture or no mother at all. I don't remember the specifics, but it was a study that was done in psychology, and in that case, conditions were specifically manipulated, but the actual observations that were taken were the same for each condition. So a lot of times in our field, observational research might be in the form of surveys or questionnaires, okay, because we are giving somebody a list of questions and then we see how they interact with those questions. For the most part, if any of you are interested in going into research in this field, you're likely going to be conducting experimental research. So this is the process of having a manipulation of variables and events in order to solve a problem. In other words, you find a variable that can be sorted into different conditions, whether it be a control group, an experimental group, maybe you have multiple experimental groups, but you have these various manipulations that you are comparing to one another. And usually the goal of experimental research is to make cause and effect inferences from the data, right? So how does this intervention cause a certain effect that can be observed between groups? Okay. Now we pull our research design largely based on the scientific method, which shouldn't be new to anybody, right? Typically we start off with an observation or a question, right? Maybe the observation is, oh, I read this research article and this is what these people did, but they had certain limitations, and I would be interested in doing a similar study that incorporates similar protocols but controls for this particular limitation, right? So you could go off of observation. Maybe the observation isn't literature related, but you just see like, oh, I have a relative who has Huntington's disease and they participated in a dance program, and their disease progression lessened. So I wonder if having dance intervention helps with disease progression of Huntington's. Right? It could be kind of on the random side and more of an original research question. But through observations, you usually create research questions, and then with those questions, they lie within a research topic area that you can then use literature from that topic area to help create your hypotheses on what you think will occur. Okay. We'll talk about hypotheses in later weeks, but for now, you would create a hypothesis. You would test that hypothesis with some experimental design. You would analyze your data, which involves both processing raw data as well as doing the statistical analysis component. And then you would report your conclusions either by writing a paper. For students, sometimes poster presentations or abstracts at different conferences might be the way that you report your conclusions. Usually you'll have a table or figures, and then a written description of those tables or figures. So tables and figures, again, are what we're working on in our activity for this week. And then based off of those conclusions, you can continue to develop your research question to become more specific, less specific. If you change directions, you create a new question altogether. And this method keeps continuing to further the research in your topic area. In terms of hypotheses, like I said, we'll go into these a little bit more in depth in some future lectures, but generally you have two hypotheses. I say two hypotheses, but let's say for the research question you have two hypotheses. Once you get into statistical testing, you will also have multiple hypotheses for various steps in the analysis. For now, we'll keep it simple, and we'll say these hypotheses are related directly to the research question. Okay, so your research hypothesis is also referred to as your alternate hypothesis. It can be denoted by H sub 1 or H sub A. I had a statistics teacher who called it the HA. I don't know why I just laughed. But basically, this is what prompts your research. Okay, so you have a research question, and your research hypothesis is going to predict what you think will happen based on the intervention that you are incorporating into your design. Usually, the research hypothesis is going to be informed by previous literature. So that's why lit reviews are so important when you're doing research, because obviously you're like, I think that smoking doesn't cause cancer. When there's like a lot of research that is linked with smoking being a cause of different types of cancers. So having a well-informed hypothesis is a very good start to have. So usually you read your literature, you research your topic area, get an idea of what's been studied, what their conclusions were, if those conclusions were applied to certain people, and then use that information to inform what you think or what you predict will happen based on the intervention in your study design. So that's our research hypothesis. Mutually exclusive to the research hypothesis is the null hypothesis, which we also call H sub 0 or the HO. That's what my other stats teacher called it. It was like ho or ha. That class was a lot of fun. Anyways, this is the statistically tested hypothesis. I put it in red because it is important and students always forget. When you run a statistical test, you are always testing the null hypothesis. Okay. The null hypothesis is usually going to be saying that there is no relationship, there is no effect, there are no differences between groups or treatments, etc. Okay, and basically it says that if there are relatively equal outcomes, sometimes it's unequal outcomes, but if we don't see the relationship that we were expecting to see, okay, any differences that we do observe are going to be due to chance or error. Okay, so that's why when we have like our p-values, which again we'll talk about later in the semester, when we talk about p-values, those are representing the null hypothesis, right? And if we have a very small chance that we made an error, which is represented by the p-value, we can safely assume that the reason that we see the results we do, right, is due to a very, very, very small random chance. Therefore, usually when we have a small chance of error, we reject the null and we say, no, these results actually occurred because of the intervention that we used in our study design. Okay, so research hypothesis is what you predict will happen, right, based on an informed decision. The null hypothesis states the exact opposite of the research hypothesis, but this is the one that is statistically tested. So another way you can think about or remember that the null hypothesis is the one is that you cannot be proven, or that you are innocent until you are proven guilty, right? So you did not do it. There is no relation, no relationship, no effect until you actually prove that there is one, which is why we always test the null. Okie dokie. We also need to talk about variables in our research, right? The independent variable versus the dependent variable. So the independent variable isn't usually intentionally manipulated by the researcher. It's also called a predictor variable or an X variable because it's usually plotted on the x-axis whenever you're creating graphs or charts. And it's usually represented in levels. So if you recall in our previous lecture, I said, what if we wanted to know some characteristic or outcome about different years in college, right? The actual year in college would be my independent variable, and I could break that down into 4 levels: freshman, sophomore, junior, and senior. Okay, so that's what we mean by levels. There are different ways that we can categorize our data. So that is a hint that your independent variable is usually going to be nominal in nature, at least for our class. There are some exceptions to this when we talk about correlations and regressions, but we'll get into that when we get there, which is after the first test. For your dependent variable, this is what you are measuring. Okay, so usually dependent variables will take on a numerical value, which means they will more often than not be considered ratio or interval data in this class. Okay, so they are what you are changing. They are basically your record of observations on what happens when you have some type of intervention. So if our independent variable is a control group and an experimental group, right, we can take measurements for some type of outcome on those. That measurement would be the dependent variable, and we can use that measurement or those measurements to see what the difference is between our independent variable groups. Okay, so oftentimes our dependent variable is also referred to as the criterion variable or a y variable because it is plotted on the y-axis. A nice way to think about independent versus dependent variables is to put them in this little formula, saying that the independent variable has some type of effect on the dependent variable, right? So whatever your manipulation is, that should have an effect. Sometimes this is also a relationship, again, if we're looking at correlations or regressions, but it's always how does the independent variable impact the dependent variable in some way, shape, or form. So we can look at some examples of this just to kind of help you out. Right? If I said the effect, or if I wanted to know what the effect of time spent in practice was on sport performance, okay, we could split this up into an independent variable where we're looking at time spent in practice. Okay, so these examples are fairly vague, right? So we could organize this however we wanted to, where we say maybe we want basketball shooting accuracy, and so we have people in basketball practice, and then we say for our independent variable, it's time spent in practice. So maybe for a handful of our basketball team, we say you're not going to practice at all. And other people, we say you're going to practice 3 hours 2 times a week, or 3 hours a day for two times a week, right? And another group, maybe we say you practice 6 hours a day for 2 times a week. Okay, so that this independent variable condition is directly manipulated by the researcher, and however many conditions we create, those are the levels of that independent variable. The dependent variable in this case, we're saying sport performance, could be free throw accuracy, right? And so maybe we could count what is a person's percentage of made baskets or made free throws. That is the variable that is actually measured, which means that's our dependent variable. Okay. It's kind of up to the researcher on how they decide to measure that variable, okay, but it is measured nonetheless. Okay. So questions to you guys, you can pause the video and kind of think about this, and then I'll say the answers after. But if we plotted this data on a graph, which variable would go on the x-axis and which would go on the y? And the second question I have for you is, what type of data would our measurements classify as? So go ahead and pause the video, think about what your answers would be, maybe write them down, and then when you play, here are the answers. So for this example, the x-axis would represent the independent variable, or our time spent in practice. The y-axis would be representing the dependent variable, or whatever our sport performance outcome is. Time spent in practice would be nominal data, because we are categorizing people into certain manipulated groups, right? So no practice, 3 hours of practice, or 6 hours of practice. And then our dependent variable, again, kind of depends on how we decide to measure the data, but let's say we were looking at free throw accuracy in terms of the percentage of shots made. Okay, that could be considered ratio data, because 0% would mean there's an absence of the measurement or they didn't make any. Okay. We could also say like that we've got ranked data in terms of whole numbers, right? Or they can assume whole numbers 1 through, maybe we ask them to shoot 10 free throws, okay? But generally should be ratio, and most of the ways that you can kind of talk about how you might have collected the measurement would point you back to the characteristics of ratio data. Okay. Another example for you guys is if we were interested in the effect of a diet on weight loss or gain. We could also phrase this as changes in weight. Okay. So using our formula, we could say the type of diet that somebody is on is what we are controlling or manipulating, right? So if we have somebody eating just their regular diet, if we specifically tell someone eat a keto diet versus a paleo diet versus a calorie restricted diet, but that follows relatively normal percentages within the calorie intake that a person is supposed to take in, right? The type of diet is what we are manipulating or categorizing or creating labels for. What we are actually measuring is the change in weight, right? So again, how we decide to measure this is completely up to the researcher. We could say, let's do a pre-weight and a post-weight, and we're looking at the weight difference. We could do body composition, where we take skin fold measurements, or maybe we do a DEXA scan, and then we observe the differences between different categories or between subjects if we're having the same people do all of the different diets. Okay. And then I posed the same 2 questions as the previous slide. So again, you can pause. Here are the answers, right? Again, x-axis is associated with the independent variable. Y-axis would be associated with the dependent variable. And then the type of data we have here is diet, or type of diet would be considered nominal or categorical, right? Meaning we've got normal diet is one category, keto is another, paleo is another, etc., etc. The dependent variable is what we're measuring, okay? So again, it kind of depends on how you want to measure your data, but most examples that you guys might think of would have pointed to a ratio type data. Okay. Hopefully those were enough examples. Now we're going to talk about the quality of research. So you have you've read the literature, you've come up with a research question, you know what variables you're collecting, how you've identified their types of data. Now we have to make sure that we are minimizing our bias as much as possible. And the way that we look at this is through internal and external validity. Primarily, internal and external validity are going to point towards our statistical inference, which we'll talk about in coming weeks, but that's basically like, does the study measure what you want it to measure, keeping in account certain variables that might affect the outcomes that you're measuring, and then are the results that you have acquired actually applicable to the population that your sample represents. So the first of the two is internal validity, which is majorly referring to the design of the study, so internal to the design, if you want to think about it that way. And this is, the definition of it is the measure of the control within the experiment that ensures results are due to the treatment applied. Okay, so the goal for internal validity is to maximize it in most cases, which means that we have to know what things in our study design may pose threats to our internal validity. Threats meaning that they decrease our internal validity. These are 4 major ones that we can think about, but this is not an exhaustive list by any means. So learning our exposure effects are one thing that could affect internal validity. Usually it's observed when you have a pre-test, post-test method, or if you're using multiple trials of a certain skill or action. The way that we control for this effect is with the inclusion of control groups. So if you can avoid doing a pre-test, post-test, and you're doing a between-subject design instead, the control group has no previous exposure to the tasks that you're asking them to do, versus the experimental group, which does have exposure. Okay, so you kind of separate things. When you have a pre-test, post-test, or a within-subject design method, where let's say we have somebody do a memory task as their baseline, we have some type of intervention, and then they do a post-test to see how that intervention affected their memory retention. Okay, we have to test using the same protocols for pre-test and post-test. Right, so maybe we're looking at a Stroop effect in pre-test and post-test. They have exposure to that initial testing. Therefore, a lot of times we can say, is there a chance that there could be learning effects when they take their post-test that will make them better at the post-test? Okay. The same thing goes with multiple trials. The more somebody does something, generally the more comfortable they feel with that task, and the better that they will do with that task. And there's some ways that we can kind of cut out the multiple trials effect thing, where we only, let's say we collect 5 trials and we take the average of it, or we collect 5 trials and we take the average of the middle 3, because the first one would probably be their worst performance, the last one might be their best one, and that would account for the change that we see between performances due to learning effects. Okay. But having a control group is going to help us differentiate how much of the changes we observe are actually due to the exposure or the treatment or intervention, and then how much are actually due to the learning or the exposure effect. So an example of this would be if we're comparing novice versus experienced people. If we said in our sample, we're not controlling for experience level, we're just taking everybody and we want to see how they do on this certain task, right? Somebody who has experience in that task, that's going to influence the performance outcome, right? Versus novice people who maybe are going to have significantly lower performance outcomes. The other thing you want to think about is maybe we want to see in pre-test, post-test, we have a mix of novice and experienced people within our sample, and we're looking at how their performance changes from pre-test to post-test with some intervention in the middle. This is problematic if any of you guys remember the power law of practice from 312. right? Novice performers usually are going to have a very rapid improvement in performance with very, very little time elapsed. Versus experienced people, they're not going to show as big of a leap because they're more in the fine-tuning stages of that particular skill. Okay, so making sure that we identify in our study design, like, or I have a great example. I did a long jump study with Dr. Wu in the movement science lab, and we specifically were taking in people who were novice performers to do a standing long jump because we didn't want previous experience in the standing long jump to affect the jump distance that was acquired. Okay, so something to think about, learning our exposure effects to a certain type of test or protocol would be important for making sure that we keep our internal validity on the high side. Another thing that we have are intervening, extraneous, or confounding variables. All of these three terms are synonymous with each other, but these are variables that are going to directly affect the results of the dependent variable, but are not included in the study. Okay, so if I, let's say, was doing a study that involved collecting EMG activity on muscles, and I was doing it in the legs, okay, that is the dependent variable I'm collecting, right? I want to see how much activity can be produced maybe by the quad muscle. But in order to do EMG activity, usually we will normalize activity based on a maximal contraction. So an example of an extraneous variable would be to make sure our instructions to our subject is that they not perform any type of intense exercise or maximal exercise prior to coming to the testing session, right? So maybe we say, oh, don't do leg day at least 24 hours before you come in, because if we're measuring the quad and they do maximal exercises or they're doing maximal power lifts the day before, their leg obviously is going to be shot, or that muscle is going to be shot, and it's going to be tired, therefore it will fatigue faster. Okay, so that's an example of an extraneous variable. And usually they should be controlled within your inclusion and exclusion criteria to make sure that those specific things aren't affecting the measurements of the dependent variable. It could also be that they're just instructions that you give to your people before coming in, kind of like the workout stuff. But also you can consider, like if you've ever given a PAR-Q questionnaire to somebody to determine if they're healthy and fit to participate in physical activity, right? Sometimes maybe you want the presence of a certain pathology. So your inclusion criteria would be you have to have this type of neurological disorder in order to participate. And if you don't have this neurological disorder, you can't participate because you would confound the variables that we're measuring for people with this specific disorder. Okay. So yes, my examples, MVIC testing. Sometimes this could be a post-test given too soon after a treatment, right? So you don't give the treatment actual time to have its effect. Usually you can figure this out in the previous literature that's been conducted on your research question. Kind of gave an example of healthy participants and injuries already. Another example would be if we're comparing a diet's effectiveness on weight loss, right? Considering, or things you might have to consider are the activity level outside of the study. Okay, so maybe we tighten the inclusion-exclusion criteria by saying we want only sedentary individuals. So that way we know their activity isn't playing into any weight changes that they see with the diet. We also might consider a person's BMI as part of the inclusion criteria. Maybe we only want people who are considered obese, which is a BMI of 30 or above. Okay, because people who are further away from their ideal weight tend to lose faster than people who are closer to their ideal weight. So that is something that you would have to consider as potentially confounding the measurements that you're actually interested in your study. Okay, so those are some examples of intervening extraneous confounding variables. Another threat to internal validity is instrument error or bias. So this is mainly error that occurs due to faulty instrumentation or equipment. Okay. Usually we can control for instrument error using a calibration protocol for the equipment. So when we use force plates, and I mean, even you guys can do this at home. If you have a scale that you measure with, you have to make sure it's zeroed before you step on it. Otherwise, like if we zero a force plate with the person standing on it and they step off, right, that zero now is their body weight. So when they step on it, they will be a ghost and they don't exist. But when they step off of it, there will be some random force that's like not there. Okay. For 3D motion capture, usually we calibrate a space to say this is the area that we're collecting in, and this is only the area that we're interested in picking up our reflective markers. Okay. Oh, these are my examples too. Yeah, another example would be like range of motion testing with an inclinometer or a bubble inclinometer. So if you guys have ever seen it, it's like a little circle that has liquid inside it, and then there's a dial that you can turn that has like angle measurements on it. When you tilt the inclinometer, the bubble moves, right? So making sure that the position that you're actually interested in, let's say it's horizontal, we line up the bubble with 0. That way, whenever you place it on a person's body segment that's tilted to a certain angle, it is relative to the 0 that you started at. The other type of error we can have is investigator error or bias, and this is related to error by the person who's actually taking the measurements. This is usually why we want to use validated tools and protocols, because if we're purely going off of observational research to collect data, let's say I wanted to see someone's reaction time and I was using a stopwatch, right? Pressing start and stop is a very subjective measurement, meaning that when I press start and stop is based, or specifically when I press stop is based on how I view the end of a person's skill. Okay. Or I could say like, yeah, they kind of met the criteria, they kind of didn't, that type of thing. So those would be types of investigator error or bias. Okay. It can be unintentional or intentional. That's like a whole other conversation. But it could be due to reading errors in reading measurements. Maybe you just write down the wrong number. Okay. A good example of this is using a vertex for vertical jump. If you add wrong in your head from the starting height to however many ticks you have based on the color of the last kind of bar that was hit. You could have tester-to-tester reliability issues. So if I was markering a person versus another person who was markering a subject, right, we could have inconsistencies that lead to investigator error, because in the grand scope of the entire project, it should be that our measurements are consistent between subjects. Okay. We could have bias when judging skills. Okay, so if a person is using a set of criteria, as long as you have some type of criteria, that would help eliminate bias. So you guys can think about this in terms of grading. I use grading rubrics, and the rubrics are based on certain components that you have included in an answer or not included in an answer, right? And being able to say like, yes, this was included, no, this was not included, is a more objective way for me to grade your papers and not insert bias into like, oh, well, yeah, they kind of got the answer, but, you know. So having some type of criteria or standardized criteria is good, especially when you're doing more observational type research, so that you're limiting how much bias you're actually inserting into your judgment of the outcome that you're measuring. Investigator bias could also be due to lack of experience using equipment. So usually When I was involved with STAR, which is the Center for Sport Training and Research, we actually had a class for it, and we would teach students how to use different pieces of equipment. Typically, we would have them log a certain number of hours before they were allowed to like do stuff on their own, and that's because you need practice doing the protocols before you can both collect both reliable and valid measurements. Okay. And then this is the intentional investigator bias, and that's falsification of data. So let's say somebody did a trial, there was something wrong with the collection period, and after the fact, so data collection is done, subject has gone home, we're like, oh crap, we didn't actually get the 5th trial, but we need 5 trials to do our calculations. What do you think it was, right? And if you just like put in a number, that would be an intentional falsification of data, right? If you're like, well, all of their other trials were kind of around this number, so I'm just going to put this so that we can keep the subject in. No. If that happens, you have to kick out that subject and just take it for what it is and get another subject to come in to replace their spot. Okay, but this is a huge no-no. You can actually, like, it could be one cause for firing, but it also could put a suspension on any research that you're able to do, if anyone ever found out. Okay. Intentional falsification of data could also mean that you use different methods to collect or analyze data for different subjects. So everything that you do in terms of the treatment of your data needs to be explicitly stated before you actually carry out the research. Usually your protocols are going to be reviewed by an institutional review board, or the IRB. They determine if your protocols are safe for your subjects, if they have greater benefits than risks for your subjects, if there are potentially any problematic things with your protocol. They might point out if your protocol doesn't necessarily measure what you're actually trying to measure. But if we were, I don't know, creating joint angles using, or let's say we're looking at hip joint angles in biomechanics. I'm assuming that none of you have ever done this before, but there are different methods to create a hip joint center, right? Because you think your acetabulum and the head of your femur, that is such an internal bony landmark that you cannot actually palpate it, because there's a lot of other soft tissues and connective tissues that are blocking the actual hip joint capsule. So there are methods that we can use to calculate where the hip joint center would actually be located, right? And let's say we used like a greater trochanter method on one person, but we used a different method on another person because, oh, this method fit this person better than it did another person, right? That is not cool. Whatever methods you use to analyze or treat your data has to be the same for every single subject. So that would also be considered an example of investigator bias. All right, so that was internal validity, or things that are within our subject design that we need to consider so that we're not negatively affecting the outcomes or skewing the outcomes of our research. The other thing that we need to consider is our external validity, which is also referred to as environmental validity. And this refers to the generalizability, I always have a hard time saying this word, generalizability of the results. Okay, so this is what we call statistical inference. Do the results that you collected on your sample represent the population you are trying to target? Okay, again, the population can be as specific or general as you want it to be, but the generalization that you make from your sample should be applicable to that given population. Okay, so if we were looking at people with Parkinson's disease in a certain age range or with a certain stage, right, because there's like stage 1, 2, 3, 4, that type of thing. If people in our sample had, like, there are certain actual tests that you can use to determine the stage of severity of a person's disease state. But if we said, oh, our target population is everybody with Parkinson's disease, and the people that we collected randomly in our sample were just stage 1 and 2 Parkinson's disease, when we present our results, we have to say, This might be applicable to everyone with Parkinson's, but because our sample was specific to, or the people that we were able to collect were within kind of the more moderate stages of Parkinson's, the generalizability of our results mainly is going to translate to those people with moderate severity of the disease, right? We can't say, oh, but this is what we observed based on our intervention. It applies to everyone with Parkinson's. No. Okay. So that's why we always want to make sure our sample is as representative of our target population as possible. So that way our results can be inferred back to the population. Some other examples of lab or things that could kind of hurt external validity is when we do lab research. You think lab research is a controlled environment, so it's great for maximizing internal validity, but it's not always great for maximizing external validity. We can also think about sample characteristics. Right, it's good to be specific in inclusion and exclusion criteria, but if the sample characteristics are too limiting, we can't generalize to as large of a population. Intervening variables can also be a thing that could affect external validity. Very similar in the ways that they affect internal validity. They're just variables that creep into your study design or that creep into the generalizability of your study design that maybe you hadn't thought of to control for. Okay. In terms of whether you want to maximize internal versus external, because they do, in these examples you can see they have a trade-off, right? The more you maximize internal validity, the more you're kind of hurting external validity, and vice versa. It's kind of up to the researcher to determine which one is more important, and you're really trying to find a happy medium between the two. More often than not, people are going to control more for the internal validity because, as you can see, there were a lot more ways that things could go wrong with internal validity. We just have to make sure when you're writing up, right, your results and your interpretations of your results that you are saying, these are the potential limitations to our study, like either pointing to the internal validity limitations, but this is also like, this is the sample that we collected, and we can generalize our results to a more specific population based on the sample we collected. Okay. So it's a give or take, but it's kind of up to you as the researcher to determine which one is more important. The last thing I want to say is the misuse, or talk about, is the misuse of statistics. So this would be including inaccurate or misleading reports of results, often due to small or non-random samples, inadequate operational definitions, as well as the presence of outliers. Okay. I like to use, for small and non-random samples, I like to use the example of when you've got like commercials that's like, Frozen is the #1 movie in the world, and you're like, okay, according to who, right? And usually it's based off of box office sales. They don't actually take surveys of everyone who watches the movie, and I mean, there could have been a ton of people who went to Frozen who hated it, you know? Let it go. Anyways, that was a bad joke. But right, it's kind of like, okay, well, what is the sample that you're collecting? You're presenting this extravagant, like, #1 movie in the world. Is it #1 out of animated movies? Because if if Frozen is the only animated movie in theaters, of course it's going to be the #1 movie because it's the only one. It's a small sample, right? Or is it the #1 movie in the world based on the movies that are in theaters currently? Again, a pretty small sample compared to all of the movies that exist over time. Okay, so smaller random samples can often skew the results that you get, and then actually presenting those skewed results could be a misuse of statistics. Inadequate operational definitions can be a thing too, so usually when you have your inclusion or exclusion criteria or the protocols that you're using, you have to be very specific about how you're defining certain terminology. Because that is going to affect the generalizability as well as the subjects and the sample that you collect, honestly. So if we said something like, oh, I wanted to exclude anybody with a lower extremity injury. Okay. Does that mean they need to be free of injury for 3 months, 6 months? Do they need to be free of injury for 3 months without any pain or without any obstruction to how they move? Right? So operational definitions, injury is a very vague term. So we have to make sure that we define and control for the definition that we want to apply in our study. Presence of outliers, this is going to be something we talk about a bit more in the next 2 weeks. We'll figure out how to test them, but usually if outliers are included in your distribution of the data that you've collected, they can skew the statistical analysis. So we usually try to get rid of them so that you're not misrepresenting what actually happened. In terms of the responsibility of the researcher, it's your guys' responsibility to report well-documented, valid, reliable, and objective results to make sure all of your measurements meet the good characteristics of data. It doesn't only include data, right, but it includes how you collect it, how you analyze it, and where you're getting your information from to inform your hypotheses, to inform your protocols. Make sure that your protocols have been validated in other research, or that a certain protocol or a tool has been used multiple times prior to you using it, unless you're going to be the first one to validate a tool or experimental protocol. That's another thing. Okay. But you also want to check on the credibility of the resources that led you to the research question and or your hypotheses. That's just conducting a good literature review, and usually you want to make sure that the sources that you are using to inform how you are interpreting your research, that they're coming from peer-reviewed sources. We'll talk about this. I don't remember what week we'll talk about this. I think it's soon. But this also directly is going to apply to your final project, because you'll have to do a short literature review on some type of question, and then use whatever is in that lit review to inform how you would create your study design. So, yeah, this by no means is an exhaustive summary of things you need to consider when designing research or when evaluating research, but they're all like kind of the main points that you should focus on when you're doing either conduction of research or reading. Okay, and we have, for my PhD program, we have an entire class every single semester that is designated just to critiquing articles, where we pick out, like, this is a problem with internal validity, this is a problem with external validity, these are the limitations of the study, this is something they could have done differently. Oh, hey, that would be a great research idea for a dissertation, let's try it out, right? So hopefully this made sense to you. We'll have a lot more examples throughout the semester that you can kind of pick apart so you can practice pulling out and critiquing peer-reviewed articles on your